Good morning from Dhaka, Bangladesh. This is the 8th lecture on lecture series of X-ray crystallography and solid state chemistry. I'm Altaf Hussain, a former professor, Department of Chemistry, University of Dhaka, Dhaka, Bangladesh. I was talking about, in the last lecture, I was talking about space group and then explained two space groups and said that we will be talking another space group and then continue our next journey. So this is the space group I'm talking in this lecture, space group P2221. That means it's a primitive space group. And then what is the crystal system then? Whenever we see this 222 point group, we immediately conclude that this is an orthorhombic crystal system. So this space group belongs to an orthorhombic crystal system. And in the international table, we see that this is number 17 space group of 230 space groups. Okay. Then we describe how how about this three figure 2, 2, 2, 1. This means that we have twofold rotation axis parallel to X and Y, and another screw axis, twofold screw axis parallel to Z. This is the feature of the space group. Then we always say that we have to also talk about the equivalent position. So looking to this figure, this is the figure which shows all the space element and point elements. So here we have to see that to visualize the equivalent position, this is a bit difficult because of automatically generated some other space element. And therefore, let's talk about it a little bit details. Otherwise, you do not understand much. So let us consider the axis parallel to Y. And it is at A is equal to 0 and C is equal to 1/4. And the starting point we take, this is the starting point, 1, which is small z coordinates. So that's a plus z, very small z coordinate, and the twofold axis at z is equal to 1/4. Z we are not seeing. We are seeing A and B in the symbol in this presentation. Z is out of this plane, that is perpendicular to this plane of projection, and Z is equal to 1/4. Therefore, 1 is at Z, 1/4 minus Z below the twofold axis. Thus, new position is that after this symmetry operation, the new position comes up to this one. Okay. The new position, rotation around the axis, therefore, at A 4 minus Z above the twofold axis, that is the Z coordinate becomes half minus Z. This is a shortened representation, which I'm showing here. Here is half minus 1. Z. If we consider the next twofold rotation to X and at B is equal to C is equal to 0. That is this passing through the origin. This axis generates position 3 prime. So this axis generates position 3, 2 prime. This axis generates this one. Okay. This from 1 and 4 triple prime. It is equivalent to the cell below 2 prime. 2 prime, this one. Cell below 2 prime. That's 2 prime. This one. This one. So now we have talked about the twofold rotation parallel to X and Y. Then we have to see that we will automatically say that it automatically creates another axis, third axis, which is twofold screw axis parallel to Z. This is automatically generated because of other two axis combination. And it's perpendicular to them. I mean, the two fold axes, one parallel to X, another one parallel to Y, and this one, two fold screw axis is perpendicular to those axes. Okay, these two axes relates to, for example, 1 and 4, how it relates, 4 prime, 1 and 4, 3 prime, how it relates. That's what we have to find out. And then we see that translation along transition position 1 by C by 2, followed by 180 degree rotation about C axis, gives us 4, 3 prime. This one gives us 4, 3 prime. Similarly, the position 2 prime and 3, 2 prime are related. So if we consider these description, then we find out that this space group P221, that is number 17, has coordinate of equivalent position, 4 equivalent position. It creates 4 equivalent position, X, Y, Z. But then another position, bar X, Y, 1 minus half minus Z. And then another position, X, bar Y, bar Z. Another position, X, bar X, bar Y, half plus Z. These are the 4 equivalent general position for this space. We have also special position with point symmetry, because we have point symmetry too, and when the generation of position equivalent position lies on this point group, then we get the spatial equivalent position. You remember that we have talked earlier. So 2A have got this position X 0 0 and X bar 0 half. 2B has got X half 0 and then X bar half 0. 2C 0 Y 1 4 0 bar Y 3 4 and 2D half Y 1 4 half bar Y 3 4. Yes, we have been talking about the difference between general equivalent position and general spatial equivalent position. Spatial equivalent position occurs only when we are operating on the symmetry element. The position operates on the symmetry element. Then we call it spatial equivalent position. Okay, now till now we have discussed 3 space groups. Number 2, number 5, and number 17. And we say that what we do, keeping these rules and regulation in mind, we can go to international table and pick up any space group we want. And in the international table, let's say international table, there we have both equivalent positions plus symmetry elements related on a particular space group. We can just practice, and then we get it very clear if we want to understand about space group. I would like to remind you that if you want to work on crystallography and want to determine three-dimensional structure of a crystal, then we have to remember very good, or we have to practice very good so that we can understand the space group properly, because space group tells us about the three-dimensional structure of a crystal. You see, with the help of space group, we will talk it later in later lectures. With the help of space group, we can always theoretically calculate out the structure factor of a crystal. If we know the space group, or if we know this crystal belongs to this space group experimentally, then with the space group description, all we take the atomic position, etc., and then we can calculate the structure factor. And from the X-ray data, we can get the observed structure factor. And comparing this observed structure factor and calculated structure factor, we can find out the structure and R value, which is a parameter to be given when you determine a structure, three-dimensional. Now I go to next class. Well, to talk about crystal structure, a very important elementary geometrical concepts are needed. Very, very important. We call that planes. There are these planes. And the direction in a crystal. What does it mean, the planes, and what this plane direct from in a crystal? That's what we have to talk. I say to you that is a very, very important concept when you determine the crystal structure. So, well, we have been talking about crystal lattice, unit cells, symmetry elements, point group, and space group in the last few lectures. So now we have to come to this concept, the planes in a crystal. So this is referred to a particular crystallographic plane or direction in a crystal are very, very necessary points, and that we have to symbolize. The crystal planes are symbolized by Miller indices. Miller indices. Okay, now we have to talk about what is Miller indices. Now, then we have to draw imaginary planes in a unit cell of a crystal. So I show here the two-dimensional unit cell first and find out what do we mean by Miller indices in two dimensions. So let us consider two-dimensional lattice. I say figure it is a two-dimensional lattice. There you see there is B direction, there is A direction. So this is, if we call this one is our unit cell, and then unit cell extended. So how do you put our concept in two-dimensional Miller indices? But what is that we if we have lattice constant A and B, and we have a set of planes intersect this axis, how this if A lattice constant divide by a translation and then call it into H parts. I mean that if we cut A lattice constant into several parts, and that's it's H parts, B like K parts. So I mean that we cut these. This is B. We cut this, these. So then we call this K parts, and if we cut like these, we call them H parts. So if we that's what is called, and if we H part and K part, then we call it HK Miller. This is two-dimensional Miller. In another way, we can express that A by H, B by K on the two axes, and this is in the reciprocal of the fractional intercepts. Reciprocal of the fractional intercept. So Miller indices in two dimension is the reciprocal of the fractional intercept. We are not taking C direction yet. We are not considering yet the three dimension. Just to show you how it works in two dimension. So let's say we take the figure A. What does it mean? That we have here this Miller indices is, if we cut like this, then it is 1 0 0 1 0 0. We cut in this direction 1. So it's 1 0 0. If we take this one, then it is B 0 0. If we take this one, note that now it is A and C. B is not shown in this figure. So if we take this one, this direction, we call it 0 0 1. Similarly, we take this one. Now again you see that it is not. It is C direction is out of this plane, B and A, and here is the origin. So if we have a plane like this, we call it 1 1 0. If you take this one, you will see that similarly we can find out in figure that these planes, these parallel planes are designated as 3, 2, 0. Mind it, here we have on this C. This C is not in our presentation. Therefore, we call it 3, 2 in 2 dimensions, two planes. It is 1, 1 plane. It is 1 plane, 0, 0, 1 plane, and so forth. Now, we extend this to 3 dimensions. Or another thing we have to remember, that when we fix our origin, let's say that I'm talking about origin, that I can take a lattice point in the origin. These are lattice points. We have talked it several times already. These are lattice points. So we take a lattice point as origin. But mind this is an arbitrary choice. Once you fix your lattice point at origin, the lattice point which is at origin, then you can see the planes can be also have negative direction. That means we can have minus h minus k. So this is also pronounced as RH bar k. So we will be talking always RH bar k when it is a negative direction compared to our origin. So I go to the next slide. Here you see that we show this is y, this is x, and therefore we are showing this plane. These parallel planes are all 1, 0, 0. Similarly, this parallel plane at 0, 1, 0. Okay, here these parallel planes 1, 1, 0, and if we take this parallel plane, these parallel planes, it is bar 1, 2, 0. That means if there is a current in negative direction of h, 1, h equal to 1. Here it is, if we take like this is the current in negative direction of h, 2 cars, and therefore we call it 2 bar 2, 1, 0. Okay, we now take it for 3 dimensions because we are supposed to determine crystal structure 3 dimension. So to get this concept, we just explain a 2-dimensional system and then come to the 3-dimensional system. You see, here, this is our origin. Let's say this is a lattice point. This is our origin. I said it's arbitrary, but you have to fix one at the lattice point. So this is the direction. Here is the direction A. We say here is the direction C. Here is the direction B. So these plane, you see, these plane we call 1, 1, 2 plane. 1, 1, 2 planes. Because you see here we have a cut at the A, 1 cut, is it not? And the B, 1 cut, and in C, 2 cuts. And therefore we call this 1, 1, 2 planes. Okay, now we have some example of a 3-dimensional solid figure. You see, we have to remember that we have to first point out our origin and then the axis direction. So here is the origin. If it is here is the origin, if this is the C direction, you see that these planes cut in C in 5 parts. If it is so, here it cuts by 4 parts. And if we go to B, it cuts by 3 parts. So what we call these planes is these parallel planes. We call it A, it is 4 cuts of 4, B 3 cuts, 4, 3, and C in 5 cuts. So we call these planes 4, 3, 5. This is how we designate these planes, these parallel planes. If we go to this one, you see, here in A direction, it is only 1 cut. In C direction, it is 3 cuts. And in B direction, it is 2 cuts. So we call it 1, 2, 3 planes. These parallel planes are 1, 2, 3 planes. If we go to this one, you can say that in this direction, A direction, there is no cut. In the C direction, there is no cut. But if we go to B direction, we see 1, 2, 3 cuts. So this is not, that means 0, not, 3, 3, not. That is the way we call about identify the plane. This one, There is no cut in A direction, so it is not 0. And there is no direction in C, so it is 0. And there is 3 cards in B, so it is 3. So not 3 not planes. These are not 3 not planes. Okay, we go further. Now we are talking about some other planes with the negative direction also. So this is a cube, this is a unit cell. So here, this shaded plane is, we call it 1, 0, 0. This shaded plane, we call it 0, 1, 0. This shaded plane, we call it 0, 0, 1. This one, shaded plane, we call it 0, 1, 1. And this plane, the shaded plane, we call it 1, 1, 1. Okay, similarly, we go for others. Now look to this. We have this solid figure, and then it is 2 cards along negative direction, 2 cards along A, 2 cards along B, and 4 cards along C. So bar 2, 4. And there it is something like that. Here it is 1, bar 1, bar 1. That is 0, 4, 2. This is what is Miller indices and the directions. Now we have been explaining what is Miller indices, and I said that Miller indices are very important point to be used in the determination of crystal structure. So we'll continue a little bit in the next lecture about Miller indices, and then go for our next chapter of syllabus. Thank you very much for today's lecture. Thank you all.